Alright, so in this tutorial we're going to pick up where we left off on solving problems involving objects projected at an angle. I'm going to redo some of the practice problems we have from the notes to set us up for two derivations. One that I'm going to do for you and the other one that I'm going to start for you and I want you to finish, especially for the activity that we want to do tomorrow. So the key to doing these problems is setting up a chart where you separate the x and y components of your information. And the major difference between this and horizontal projectile motion is that our velocity, initial velocity has an x component and a y component. They go by the cosine and sine respectively. So in this problem where we're kicking a football at an angle and a speed, and that's all you're given, we can address three important parameters: time in the air, range, and maximum height. You just got to be able to pick out the right information. So time in the air, we should know by now, is a vertical phenomenon. So I have 1, 2, 3 pieces of information I know about vertical motion. I know initially it was going upward at v sine theta. I know the acceleration is always downward at negative g. And the third piece of information that might not be as obvious is that our final velocity just before it's the ground is the same as the initial but in the opposite direction. So the equation that I would want to use there is essentially time equals my final minus initial all over the acceleration. Alright, so if I plug in my numbers, and this would really be v sine theta, negative v sine theta, how about I do that? How about negative 2v naught sine theta on top divided by negative g? So those become positive. So if I plug in the numbers, and you can do that yourself, we will see that this is 3.86 seconds. Now that I know how long it's in the air, it's fairly easy to find my range. The range is an x direction. We go to our x. We now know this is 3.86. So I've got the speed in the x direction. I've got the time, and I know the acceleration is 0. So the equation I want to do is v cos theta, all right, vx times time in the air. V is the launch speed. That's the 33, cosine of 35 times time. And we'll get around 104 meters. And then lastly, height, all right, that's y max. Okay, so again, we're going to go to the y column, and I can use this information. I also know that the time, while the full time is 3.86, it's 1.43 for the half time. So that gives you two choices for equations. I'm going to go base mine on not using the time and basically say at the peak this is going to be 0. So I know that the initial speed is v sine theta, so it's really just y max is equal to v sine theta quantity squared divided by 2g. Okay, and that comes from the equation vf squared equals v naught squared plus 2a delta y. I want the y components, and as we said, this is 0. This we can calculate as v sine theta, square it, and then we have the 2 times the acceleration, which is just 2g. Plug in numbers, we get 18.3 meters. Okay, so it goes fairly high and very far. And if we change to 55 degrees, how would the following change? Well, 55 is more vertical than 35, so this is going to go up. Horizontal is less horizontal, so it's going to go down. Time in the air goes with the vertical, so that's going to be greater. Height is going to be greater because it's launched straight up. And the range part, you got to think about a little more. How does 55 compare to 35? Well, they're complements, so those will be the same. All right, so that's the standard stuff we've been doing. Now we want to take this. We want to develop two other equations that simplify some of our calculations as well as give us new insight into projectile motion in its most general form. If we look at this problem right here, finding the range, we see we have to do 2 steps. We've got to find the horizontal component of velocity, and then we have to do a separate calculation for time in the air based on this equation right here. Wouldn't it be nice if we could find a range without having to find time in the air first? In other words, essentially combine both those equations. This would also allow us to find the angle that you'd have to launch something if you were given a range. Okay, so if you're told that something is a few hundred meters away and you say set your cannon, set your launcher at a certain angle, this would be the way to do it. So we're going to develop this equation, which is fairly straightforward, also involves little trig identities that you may have forgotten. Alright, so our goal in this first problem is express range delta x as a function of our initial speed, that's a given, g, which we know, and let's add to that theta, the angle which we launch it. Okay, so we're not going to do it as a function of time. We want to get rid of that. And this only works if our initial height is equal to our final height. So that's an important stipulation. Okay, so where do we start? Like any derivation, we want to start with an equation that at least solves for what we're looking for, and that's x, right? So we already know that our range is essentially Vx, which is V cosine theta, times time, okay, in the air. I don't want time in the air in my equation, so I'm going to substitute it out. So I need an equation for time in the air. Well, if we go back to the previous problem without reinventing the wheel, we see that time in the air is twice our vertical velocity, which is V sine theta, all over g. So if we substitute that into here, we've got delta x equals V naught cos theta times 2 V naught sine theta all over g. Okay, but in essence we're done, but we can see we have cosine theta and sine theta, so we want theta in two different operations. So let's try to simplify. So the V naught times V naught right here and here, that gives us V naught squared. I've got the g in the denominator, so I'm going to leave that there, and then I'm going to write it as 2 sine theta cos theta. Okay, so you might wonder, why did I put the 2 in front of the sine theta cosine theta? It doesn't matter where I put it, it's the commutative law, because that lets me recognize a trig identity. So you should have learned this in A2 trig. Maybe you haven't got there yet if you're taking A2 trig, but definitely if you've been pre-calc, you should know this. So if you don't recognize it, let me tell you. So our equation then becomes x equals V naught squared all over g. So let me stop there for a second. That tells us something important, that your range goes by the square of your launch velocity. So you double the velocity which you launch something, you can get 4 times the range. You wouldn't expect that. In fact, if you look at this equation right here, it would seem to suggest that they're linear, but hidden in there in the time is another v. Okay, so that's how you can rationalize that it goes by v squared. So what's the rest of it? Well, 2 sine theta cos theta is nothing more than a sine of 2 theta. All right, that reveals something else that's interesting about range. If I want the maximum possible range for a given velocity, then I want the sine of the angle to be as big as possible. Well, what the sine of what angle is the maximum is 90 degrees. And the sine, so twice my angle, the maximum would give me 2 theta with 90, so theta is 45. So there's our proof that 45 gives us the greatest possible range under ideal conditions. And secondly, when I do sine of 2 theta equals some number, let's call it x, okay, there are 2 solutions to that. And both those solutions are complements of each other. So I'll leave it to talk to math people to show why that is, but that is where we see that 2 angles give us the same range are complementary. Okay, so this is a really nice equation. Very, very useful. So we can go down here and do a problem. Let's say a cat is fired out of a cannon with a launch speed of 50 meters per second, right, at an angle of 40 degrees. What's its range? I can now do that in one step. Whoops, that should be v squared all over g sine, and I'm going to put in 2 times 40 degrees. So really the sine of 80. So if you're in degree mode, you punch that out, you get around 250 meters. Okay. What I'm not solving for here is, what if I told you the range, I gave you that, and I asked you to find the angle? You could do that as well. All right, we'll do B and C in class. So this leads us to the last equation, last derivation we'd like to do. We want to know, it's useful in many applications, to, if we draw a parabolic arc, to know how high we are, let's say y, as a function of x. In other words, not after a certain amount of time, but after we've gone a certain amount of distance. Okay? In fact, the activity we're going to do tomorrow is really built along that. So our next derivation is express height, y, as a function of x. So where do we start? Well, the only equation we really have that helps us find height is the one that says the height equals our initial velocity in the y direction, so I'm going to go right in there with v sine theta, times the time in the air, minus 1/2 gt squared. So I put the minus in there because g is downward. So that equation will give us height at any given time. but I don't want it in terms of time, I want it in terms of position. So what I'm going to do is get rid of time and put in something about the horizontal position. In order to do that, we need an equation that relates those two things. And the equation that we know that relates horizontal distance and vertical and time is v cos theta times time. Okay, so this is what I want you to try on your own. I want you to take this equation right here, solve for t, and then substitute into here and simplify where you can. It's still going to look messy. It's not going to reduce down to some simple little equation, but you should come up with an answer that we'll find useful in class tomorrow. All right, good luck with that. Give it an honest effort.